In this video, we're going to continue our discussion of equilibrium with a discussion of the reaction quotient. Now, the reaction quotient is given a symbol Q, and that Q can be determined or is determined in the same manner as the equilibrium constant, but it's not at equilibrium. It's going to tell us where the products and reactants stand, and we're going to be comparing it to the equilibrium constant to see which direction it's going to need to shift in order to get to equilibrium. And again, this uses values for concentrations other than equilibrium. It's not at equilibrium. The only purpose of finding Q is to compare it to K. I want to say that again because it's really important. The only purpose for finding Q is so that we can compare it to K. Now, what happens when we compare it to K? What can we tell? Well, first of all, if Q is equal to K, if Q is equal to the equilibrium constant, then the system is at equilibrium. However, if Q is greater than K, now let's remember how both Q and K are found. They are both the products over the reactants. So if Q is greater than K, that means the products are too high. If Q is too big, the products are too high. And if the products are too high, we're going to need to shift it towards the reactants. The reactants are to the left. So if Q is greater than K, the reaction will shift left to reach equilibrium. If Q is less than K, think about what that means. If Q is too low, that means the products are too low. And if the products are too low, we need to make more. And so in order to make more products, we need to shift the reaction to the right in order to reach equilibrium. And that's exactly what we're going to use to answer questions when we find Q about how to shift to get to equilibrium. Now, one of my students once said, well, look at the greater than and less than signs. And we used to call these alligator mouths whenever I was in school, but the alligator mouth is open and chomping towards Q in the first case, which means it's going to shift that direction to the left. And in the second instance, the alligator mouth is open towards K, and I would attempt to draw the rest of the alligator, but that would be folly. So with the alligator mouth open towards K, it means it's going to shift in that direction to the right, and that's just a little quick way to make that determination if you're dealing with a multiple choice where you don't need any explanation. But if you need an explanation, you've got to talk about what happens in terms of the products and the reactants. So how would that play out in a problem? Well, let's look at this one. It says that we have the value of K as 6 times 10 to the negative second at 500 degrees. So that's a piece of information that we have. In an experiment, and usually I don't circle those underlying pieces of information, in an experiment we've got 0.5 moles of nitrogen, 1.0 times 10 to the minus second moles of hydrogen, and 1 times 10 to the negative fourth moles of ammonia. And this is where I need to find my volume of my flask and put a little smiley face by it or something, because I've got to make sure that anytime I'm dealing with equilibrium, remember, I've got the values in molarity. Now, you got to love, this is like a major smiley face, because when it's a 1 liter flask, the number of moles is the same as the molarity of the substance. So that makes it nice. So that's true in this instance. It wants to know in which direction the system proceed to reach equilibrium. As soon as it asks you what direction it will go in order to reach equilibrium or which direction it will shift, you know you're dealing with a Q problem. Find Q. And we know that Q is found the exact same way as K. And if you remember from our previous discussion, in this case, that's going to be, since all of these are gases, all of them are included, the concentration of NH3 squared, products over reactants, divided by the concentration of N2 and the concentration of H2 cubed. So plugging those values in, we have 1.0 times 10 to the minus fourth and that's going to be squared. I'm not including units because they're not involved in our Q or K values. 0.50 molar for our nitrogen. 1.0 times 10 to the negative second for our hydrogen, and we're going to cube that value. Make sure when you do this in your calculator, you do it correctly. Either find those values ahead of time or just do it the long way. Just put in 1 times 10 to the minus fourth, and you could go ahead and square that if you want to, but when you start plugging in the rest of it, this is the way I would do it. Divided by 0.5 and divide by 1 times 10 to the minus second, divided by 1 times 10 to the minus second, divided by 1 times 10 to the minus second. Different calculators are going to treat that cubed differently when it's on the bottom, and you want to make sure that you calculate it correctly. If you do calculate it correctly, you should come up with the fact that Q is equal to 0.020. Now remember, the only purpose of finding Q is to compare it to K. Going back up in the problem, we see that K is 6 times 10 to the negative second. Well, I can't compare. Some people are maybe better at it than me, but when I'm comparing numbers, I need them to both be in the same type of number system. So if Q is in standard notation, I need for K to be in standard notation also. So this is 0.06. We could put a 0 at the end, I guess, if we wanted to. And when we look at these values, then we can see that comparing Q to K, Q at 0.02 is less than K at 0.06. So what does that mean? It means that our reaction, if Q is too small, Q is smaller than K, that means we need more products. And if we need more products, that means we're going to be shifting the reaction towards the products, which means shifting to the right. Also, our little shortcut of the open alligator mouth to the right. So it is not at equilibrium. We're going to shift right to reach equilibrium. And that's how we use Q.